afternoon, everyone. Let's wait for 5 minutes before we start the session. Okay, so today we will be discussing the assignment problems of week 9, which involves questions related to functions of several variable, specifically optimization corresponding for the function of several variables. So let's start with first question. Before solving it, I'll give you an idea how such problems are actually tackled. So yeah, question number one. Let f from R2, that means it is a function of two variables, to R be defined as fxy is equal to x square plus y square for every xy in R2. State whether true or false. The function f has exactly one point of local maxima. One point of local maxima. Now, what do we mean by a local maximum? So, a point mm, x naught, y naught in R2 will be is said to be a point of local maximum, and in bracket I'll give the equivalent definition for local minimum if there exists some neighborhood, uh, I'll write it properly, neighborhood of x naught y naught, that means a region that contains the point x naught y naught, such that neighborhood, let me denote it by n, such that the value of the function fxy. Now, for the local maximum, the values in the neighborhood of that point x naught, y naught should be less than equal to the value at x naught, y naught. So, fxy should be less than equal to fx naught, y naught for every xy in n. That means around a point, the function takes values lesser than the value at the point x naught, y naught. That gives us a trivial idea. That's why we can call this point x naught, y naught to be a local maximum. And simultaneously, for local minimum, we should have fxy greater than equal to fx naught, y naught for every xy in n. Now, this was the definition. So, so how to look for such local extremums? We should have some procedure, direct method, so that we can at least get some ideas. So, as in one variable, we all know that in order to check maximum minimum, we first look for the critical points and then see whether they will be maximum, minimum, or the saddle point. So here also we start with critical points. Um, Solution. So in order to find local maximum slash minimum of a function f, we follow the following steps. The following steps are we can say we approach the following steps. So the step 1 is to find critical points. So what are critical points when it comes to function of several variables? So the points where all the partial derivatives are zero simultaneously. That means, that is, we look for points. So for example, in this case, when we are working in function of two variables, we look for points x comma y in R2 such that the partial derivative of f with respect to x at this point is 0 and the partial derivative of f with respect to y at these points is 0. Now, having done so far, then we see whether these critical points are points of maximum, minimum, or saddle points. Further, the next step, step 2, is to evaluate uh, d. D is equal to, so it's the second partial derivative del 2f by del x square, del 2f by del y square at point xy. Now these points are the critical points, minus del 2f by del x del y square at the above found critical points. So we firstly start with looking for critical points, and then at those critical points, we look for the value of this d. So based on the value of this d, we further check whether the points, whether which point is maximum, local minimum, or a saddle point. So next step, we can say, now this d can either be positive, negative, or 0. There are only three possibilities. Either d is positive, d is 0, or d is negative. Now if d is positive, in that case, we get sure that the critical point will be either maximum or minimum, local maximum or local minimum. And in this case, suppose d at some x naught, y naught was positive, then we look for the partial derivative del 2f by del x square at this point x naught, y naught. Now, if this is also positive, then we say that this x naught, y naught is local minimum. So it's something similar to the second derivative test as we used to do in the one variable case. And if del 2f by del x square at this point x naught, y naught, this is negative, then x naught, y naught is local maximum. Now you might think that what happens if the second derivative is 0? So you can notice that if this was 0 at some x naught, y naught, then obviously the value d, which is del 2f by del x square, del 2f by del y square minus del 2f by del x del y. Now this term was 0 at point x naught, y naught, at point x naught, y naught. X naught, y naught. Now since this first term was 0, we would be left with just minus del 2f by del x y del y square. Then it can never be positive. Therefore, this case won't happen. So basically, in this case, this second derivative with respect to x would be either positive or negative. The case 0 cannot happen. Therefore, if d is positive and further the second partial derivative with respect to x is positive, then we get the local minima. And if the second partial derivative is negative, in that case we get local maxima. Now what happens at d equals to 0? In this case, this test fails. So this test can't tell you anything. You cannot judge anything on the basis of this test. The test fails in this case. So precisely when d is equal to 0, you further need to look what the function will actually be. So a good idea would be just try to plot the function if you could and look for some points. That's the only way you can uh, move ahead in the case when d equals to 0 at some critical point. You can't say anything. And if d is negative, in that case, we get a saddle point. That means a point where the concavity changes, but it is neither maximum nor minimum. Okay, I hope this idea is clear how we look for critical points and the local maximum minimum for function of several variables. Now, in our case, we have this function fxy equals to x square plus y square. So, let's start with the solution. So, we are given our function fxy is equal to x square plus y square. So, if you want to plot this function, you have z equals to x square plus y square. So if this is the z axis, so it's a collection of all the circles within every positive possible radius. So all the points like this. So basically this is something like this. So clearly you can see that it has a local minimum, sorry, global minimum, but it will blow up. It's increasing everywhere. So you can't look for local maximum. But what the statement was given, the question was said that the function has exactly one local maximum, which is clearly not visible through plotting the function. Further, if we want to use our standard methods, we start with the critical points. Let's look for the critical points. So del f by del x, this is 2x and this is 0 if and only if x is equal to 0. Simultaneously, we should get del f by del y equals to 0 and this happens if and only if y equals to 0. Therefore, both the conditions hold simultaneously only at the point 0, 0. Therefore, we have just one critical point, the origin. So the critical point is just the origin. Now at 0, 0, let's evaluate d. What was d? D was del 2f by del x square, del 2f by del y square minus del 2f by del x del y whole square. Now from here you can see that the double derivative with respect to x is just 2, and again with respect to y also this is just 2, and if you differentiate this by y you'll get 0. So this is 4, which is strictly positive. So we all know that when d is strictly positive, we can look for local maximum or minimum. So in that case, the function in that case we need to see what is the sign of the second derivative with respect to x at that point. Now del 2f by del x square at the origin. In fact, everywhere this is equal to just 2, which is positive. That means by second derivative test, the function f has local minimum. In fact, in this case, it is turning out to be global minimum. Local minimum at 0, 0. And f does not have any maximum. Therefore, the given statement was false. I hope it is clear how we can conclude this solution using either the graph of the function, or in fact it's not necessary that you'll always be able to plot the graph of the function. So it's always better to use the second derivative test. And yeah, this is the second derivative test. Firstly, we start with looking for critical points, then evaluate this d at all these critical points, and based on the basis of the sign of this d, we further conclude whether we get maximum, minimum, or saddle points. So please go through the solution again. Then we'll move to next question. If you have any doubt, you can ask. Okay, so if there is no doubt, we can move to next question, which is almost similar. We need to use the same idea. So question number 2. Let f be a function of two variables giving real values, be defined as fxy equals to x to the power 4 plus y to the power 4 minus xy for every xy in R2. State whether true or false the origin is a saddle point of the function f. So let's see what happens at origin. Firstly, we'll start with looking for the critical points. Now clearly this you can't easily plot this function. It's not that easy. So it's good to use the second derivative test. So let's see if we are actually able to use it or not. So we start with looking at the critical points. So critical points are the points which gives all the partial derivatives 0. So step 1, we look for critical points. So del f by del x, this is equal to 4x cubed minus y, this is 0. If and only if, yeah, the points lie on the line 4x cubed minus y equals to 0. And simultaneously, we should have del f by del y equals to 4y cube minus x should be equal to 0. That means we want both the conditions 1 and 2 to hold simultaneously. That means we need to find x and y that satisfies both the equations. That means we need to find the solution. So finds x and y such that 4x cube minus y equals to 0 and minus x plus 4y cube equals to 0. We'll just use the substitution method to find the point of intersection. So yeah, by second equation we have x is equal to 4y cube. Now using it in equation first, we get 4y cube minus y equals to 0. So from here we get 4 to the power 4, y to the power 9 minus y equals to 0. Y 4 to the power 4, y to the power 8 minus 1 equals to 0. That means either y equals to 0. Now if y equals to 0, then by equation first and second, x should also be equal to 0. Or we have, so one of the critical point is origin. What happened? So the origin is a critical point. If you want to look for other critical points also, so just in that case, we'll solve rest of the thing. 4 to the power 4, y to the power 8 minus 1 equals to 0. That means y to the power 8 is equal to 1 upon 4. In fact, 2 to the power 8. So that gives us this y is plus minus 1 by 2. And hence x, which is equal to 4y cube, 4 times plus minus 1 by 2 cube. This will be 4 plus minus 4 times 1 by 8. So x is plus minus 1 by 2. So from here, the list of all critical points 0, 0. Then if x is 1 by 2, in that case y should be 1 by 2. Yeah, for y equals to 1 by 2, x is 1 by 2. For y equals to minus 1 by 2, x is minus 1 by 2. So these are the three critical points of the function f. So since they're asking just for origin, let's see what happens at the point 0, 0. So we have t, the second derivative. So from here, you can see that the second derivative del 2f by del x square, this is 12x square, and del 2f by del y del x, this is equal to minus 1. And from here, del 2f by del y square, this is this again differentiating this function by y. So this will be 12y square. So I'll just write it in red from here. D is 12x square times 12y square minus 1 square. That means 144x square y square minus 1. So since d was 144x square y square minus 1, at origin this will be minus 1. And what that means, this d is strictly negative. What happens when d is negative? The critical point turns out to be the saddle point. That's what they were saying. That's what was stated in the problem. statement says that origin is a saddle point. Yes, the point origin is a saddle point. A saddle point. Hence, the given statement is true. Please go through the solution again if you have any doubt at any point, or if you feel that I missed something or I could not explain something clearly, you can tell me. Okay, so if there is no doubt, we can move to next question. In next problem, we'll be using the method of Lagrange multiplier, which is used in order to optimize a function when we have some constraint. So we call it constrained optimization. So let's see how this method works. Question number 3. If a rectangular box without lid, that means the top of the box is not there, is removed, is to be made with 12-meter square cardboard. That means we are given the surface area except for the top part. Then the maximum volume, we need to maximize the volume, maximum volume of the box is 1 meter cube, 2 meter cube, 3 meter cube, or 4 meter cube. So if we consider this to be the rectangular box, and this, it doesn't have the topmost part, so this is open from up. So if we assume this length to be x, breadth to be y, and this height to be z, let the length be equals to x meter, the breadth, or we can say width, no? The width of the cardboard is y meters, and the height is z meter. So we are given that the surface area is 12 meters square. That means 2 times, see, xy is just 1 time, so the surface area will be xy plus 2 times yz plus zx. This is given to be equal to 12. So we call it the constraint. We need to maximize the volume. So what do we need to find? We need to maximize the function. What is the volume of the cuboid? It is equal to xyz. We all know that the volume of the cuboid is length into breadth into height, length into width into height. So we need to maximize the volume provided this constraint is satisfied. Subject to, we call it in this way, subject to the fact that xy plus 2yz plus zx, this is equal to 12. So this is what we need to solve. So here we will be using the method of Lagrange multiplier. What does it say? It says that if we construct a function, define the function L, which depends on x, y, z, and some parameter lambda, which is equal to fxyz plus lambda times, or instead we can say minus, whatever, lambda is just a real number, lambda times gxyz, where this gxyz is nothing but the constraint, where gxyz, this is equal to xy plus 2yz plus zx minus 12. So if we need to maximize or minimize a function f with respect to the constraint that gxyz equals to 0, in that scenario we construct this function L, and the critical points are given by, then the critical points are the points such that the partial derivatives of L with respect to x, y, z, and lambda all are 0 at those points, such that Lx at that point 0, which is equal to Ly, Lz, L lambda. Basically, yeah, we need to look for points x naught, y naught, z naught, and lambda naught, such that all these partial derivatives are 0, and in fact we get maximum minimum on these points only. So basically we need to find these points x, y, z, and the value of the function at these points. Only these points will give us either maximum, minimum, whatever that's possible. So for our case, we have this L x, y, z lambda. This is equal to f x, y, z. That means x, y, z plus lambda times x, y plus 2 y, z plus zx. Sorry, minus 12. So firstly, the partial derivative with respect to x, Lx, this is equal to yz plus lambda y plus 2z. This is equal to 0. That means our first equation is yz plus lambda times y plus 2z equals to 0. We mark this as 1. Similarly, 0 equals to Ly, which is equal to zx plus lambda x plus 2y. Sorry, that's will be 2z. 2z. So second equation is zx plus lambda x plus 2z equals to 0. This is equation 2. Then we have 0 equals to Lz, which is equal to xy plus lambda 2x plus 2y. So from here we get our third equation, xy plus lambda 2x plus 2y equals to 0, and the derivative with respect to lambda. Did I mention lambda also? This is equal to, that's just the fact that it satisfies the constraint. So this will be xy plus 2xz plus 2yz equals to 12. This will be our equation 4. So let's solve these 4 equations. So firstly, by first and second, you can see that, let me use different colors. By first and second, if we solve first and second, so in first and second we find the value of x and y with respect to z and lambda. So we get y equals to, this will be equal to, yeah, by first we have y times z plus lambda plus 2 lambda z equals to 0. That gives us y equals to minus 2 lambda z upon lambda plus z. And by equation 2, exactly in similar way, we have x z plus lambda plus 2 lambda z equals to 0. That gives us x is equal to minus 2 lambda z by lambda plus z. Now this tells us that both x and y are equal, and in fact they are equal to minus 2 lambda z by lambda plus z. Now using this in equation 3, we'll end up with an equation that involves just lambda and z. So by third, in equation 3, what do we have? xy minus, so 0 is equal to xy minus, sorry, plus lambda times 2 lambda x plus y, which is equal to minus 2 lambda. In fact, yeah, since we do not even have z, so just use the fact that x equals to y. So this will give us x square plus 4 lambda x. That means x times x plus 4 lambda is equal to 0. Either x is equal to 0 or x is equal to minus 4 lambda. Now if x is equal to 0, that will give us that y is also equal to 0. And then by equation first or second, whatever you want, you'll get that z is also equal to 0. By first, z is also equal to 0. So one of the point is 0, 0, 0. Then if x is equal to minus 4 lambda, in that case y will also be equal to minus 4 lambda. And since yeah, this, if I mark this as equation 5, okay, by 5 we get minus 2 lambda z upon lambda plus z equals to minus 4 lambda. So from here, this lambda gets cancelled out, minus 2. So, sorry. So we are left with z equals to 2 lambda plus 2z. That means z equals to minus 2 lambda. So x equals to minus 4 lambda, y equals to minus 4 lambda, and z equals to minus 2 lambda. Still now we haven't used this equation number 4. So next we'll use this equation 4. Then by equation 4, we have 12 equals to xyz. Oh, sorry, xy plus 2xz. Yeah, this one. Xy means minus 4 lambda minus 4 lambda xy plus 2 times xz. 2 times, yeah, xz. X is minus 4 lambda, z is minus 2 lambda plus yz, which is minus 4 lambda minus 2 lambda. So this is equal to 16 lambda square plus 2 times 8 lambda square plus 8 lambda square, 16 lambda square. So this is 16 plus 32, 48 lambda square. And on the left hand side we had 12. That means lambda square is equal to 1 by 4. That means lambda is plus minus 1 by 2. So if lambda is 1 by 2, in that case we get x. X was minus 4 lambda. So minus 4, 1 by 2, minus 2. Y will be also minus 2, and z was minus 2 times lambda. So that will be minus 1. So next point is, this will be minus 2, minus 2, minus 1. And if lambda is equal to minus 1 by 2, in that case, x will be 2, y will be 2, and z will be 1. Now, the critical points. So all the possibilities of x, y, z in the case of maximum or minimum are either this, all three of them are 0, this first one, or it's minus 2, minus 2, minus 1, or 2, 2, 1. But we all know that we started with x, y, z to be the length, width, and height, which cannot be less than equal to 0. But since x, y, z all are strictly positive, so the only critical point possible is 2, 2, 1. And at that point, the value of the function fxyz, this is, what is this? 4. Therefore, the maximum possible volume is 4. The box is 4 meter cube. Therefore, option D is correct. So I hope the solution was fine. You understood how we use the method of Lagrange multiplier. So the idea is to firstly construct this function L and then look for the critical points. And at those points, we find the values of the function. In fact, you can see that at rest of the critical points, the value was actually lesser than. So in this case, in this case, fxyz will be 0, and in this case fxyz will be minus 4. So the maximum value is coming out at 0.221, and in fact other two cases are also not even possible where in the real life scenario. So therefore the maximum possible volume of the box will be 4 meter cube when the surface area is fixed. So please go through the calculation again. I might have done some mistake. It will be always, it's always good to have some check, no? If you also do it by yourself, I'll be sure that yeah, whatever I did was right. So the main complication is to find the critical point because we have so many equations now. Mhm. I'll wait for 5 minutes. I'll come back. Yeah, I'll come back in 2 minutes. Just see, go through the proof again. Okay, so if there is no doubt, we can move to next question, which is on double integration. So question number 4, the double integral of the function of the function fxy equal to x e to the power minus y over the domain the domain 0, comma 2 cross 1, comma 2 is equal to first option e to e minus 1, e minus 1 by e square, or 2 e minus 1 by e square. So it's just calculative. I hope you all are very well aware of that high school integration, how you used to do it. So in the case of two variable, all you need to make sure is how to take the limits of the integral. So in this case, our domain is 0, comma 2 cross 1, comma 2. That means our the values of x are from 0 to 2 and y is between 1 and 2. So that means if this is the x-axis, this is x equals to 1, x equals to 2, y equals to 1, y equals to 2. Sorry, we want x from 0 to 2. No? So this is x equals to 0. This is x equal to 2. So x lies in this region. And y, this is y equals to 2. This is y equals to 1. So the overall region is this. Okay, that means if I call this as r, we need to find the integral over r of the function fxy, which is x e to the power minus y dx dy. So putting the limits, value of x is from 0 to 2, value of y is from 1 to 2, x e to the power minus y dx dy. Now since it was dx first, that is why we first put the limit of x, the values of x, the range for the values of x. So next is to just use our high school mathematics to integrate it. Now, firstly, we need to integrate this from 0 to 2 x e to the power minus y with respect to x. So in this case, this e to the power minus y will be treated as a constant. So I can take it outside. So this will be 1 to 2 e to the power minus y, 0 to 2 x dx and dy. So this will be 1 to 2 e to the power minus y, and what is the integral of x? X square by 2, 0 to 2. So this will be 1 to 2 e to the power minus y. After putting the limits, it will be 4 by 2, that means just 2 dy. And what is the integral of e to the power minus y? Minus 1, 1 to 2. So the power minus 2 minus e to the power minus 1. So this is 2 times 1 by e minus 1 by e square. So taking this 1 by e outside, it's 1 minus 1 by e. And this taking e as the LCM. So this is 2 e minus 1 upon e square. That means this option D is correct. 2e minus 1 by e square. Yeah, please go through the calculation again. In fact, let's do one thing. I'll write the next question. You do it yourself and then let me know. Because this is just calculation. I'll write the next question. Wait for 5 to 10 minutes. I would like you to solve yourself first. And then, of course, I'll discuss how it can be solved. Okay. So next we have question number 5. The double integral of the function fxy equals to y sine xy over the domain 1 comma 2 cross 0 comma pi is equal to 1, 2, 0 or pi. Just go through the solution of the previous question first and then try to solve this question number 5 yourself. I'll wait for 5 to 10 minutes. I'll give you some time. You can. It's not that tough. I think if once you go through the solution of question number 4, exactly you'll get the idea how we need to solve question number 5. Okay, so let's solve this. We are given that our x lies between 1 and 2 and y lies between 0 and pi. That means we need to find the integral if this is y sine xy dx dy. So x is from 1 to 2, y is from 0 to pi. So firstly, if we are integrating with respect to x, so in that case, this y is constant. So I can take that outside, y. Integral of sine is cos minus cos xy upon y, 1 to 2 dy. Now this y gets cancelled out. I get minus 0 to 4, putting the limit cos 2x, sorry, 2y minus cos y dy. So this is just 0 to 4 cos y dy minus 0 to 4 cos 2y dy. Now since integral of cos is sine y, sorry, this is not 4, this was, oh, this was pi. What am I doing? This is just 0 to pi, 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 pi. 0 to pi minus sine 2y upon 2, 0 to pi. Now since sine pi is 0, sine 2 pi is 0, sine 0 is 0, everything is 0. Therefore, option D is correct. Sorry, option C. This is equal to 0. Yeah, I hope this solution is fine. Okay, then, if this is fine, we can move to next question, which is again an application of this method of Lagrange multiplier. Question number 6. The maximum value of the function of the function fxyz equal to x cube plus y cube plus z cube, subject to the condition or the constraint that x plus y plus z equals to 6 is equal to, I think there is some typing mistake in this question. Instead of maximum, it should be minimum, because maximum value is coming out to be something which is not in the options. Well, let's discuss it and we'll conclude then. Okay, so we'll be using exactly same the method of Lagrange multiplier. We start with defining the function L, x, y, z. This is equal to x cube plus y cube plus z cube plus lambda times x plus y plus z minus 6. So differentiating with respect to x, we get 3x square plus lambda equals to 0. Similarly, 3y square plus lambda equals to 0. 3z square plus lambda equals to 0. And x plus y plus z equals to 6. So yeah, I'll write in bracket how we get this. Lx equals to 0. This is Ly equals to 0. This is Lz equals to 0. And this is L lambda equals to 0. Okay. So from here we get this x square is equal to minus lambda by 3. Similarly, y square is equal to minus lambda by 3, z square is equal to minus lambda by 3. And from there, we have several cases. So, case 1 will be when x square, so that gives us that x square is equal to plus minus under root minus lambda by 3 y square, because lambda we do not know whether what it is. It need not be positive. In fact, in this case, for everything to be clear, this lambda should be negative. So yeah, we assume that this lambda is negative. In fact, we'll find the value of lambda also. From here, y square is plus minus under root minus lambda by 3, and from here, z square is equal to plus minus under root minus lambda by 3. So all the terms x, y, and z, all these three have two possibilities. So overall, the point x, y, z will have 8 possibilities. So because we have two possibilities for x, two for y, two for z, so eventually it can have 8 cases. So if I say alpha is equal to under root minus lambda by 3, so the possibilities for x, y, and z will be, first case, this is equal to alpha, alpha, alpha. Uh, let's just write all the cases. Or this will be alpha, alpha minus alpha, alpha minus alpha, alpha minus alpha, alpha, alpha. In all these three cases, what's happening is one of them is negative. Then we have the possibility when two of them are negative. So alpha minus alpha minus alpha minus alpha, alpha minus alpha, and minus alpha minus alpha, alpha. And the last possibility is that all of them are negative. So in all these cases, we have one more condition, this x plus y plus z is equal to 6. So let's mark this as C1. I'll mark it with red. For case 1. So case 2, case 3, case 4, case 5, case 6, case 7, and this will be case 8. So in C1, x is equal to y equals to z is alpha. So by equation star, by star, we get 3 equals to 3, no, not 3, 6. 6 equals to alpha plus alpha, that's 3 alpha. So that gives us alpha is equal to 3. And what was, sorry, alpha is equal to 2. And what was alpha? Alpha was under root minus lambda by 3. This is equal to 2. Squaring both sides, minus L lambda equals to 4 times 3, 12. Lambda is minus 12. That means x equals to y equals to z equals to alpha, and alpha is, since lambda is minus 12, under root 12 by 3, 4. So this is again two possibilities. It's either plus 2 or minus 2. Okay, so that means, but yeah, in this case we have taken specifically alpha to be positive, no? Yeah, so only the positive case will be applicable, because negative cases will be dealt later. in other cases. So this is just plus 2. So in that case, xyz is 2, 2, 2, and fxyz will be, what is the function? X cube plus y cube plus z cube. That means 8 plus 8 plus 8. 24. Okay, let's see what happens in second case. In C2, we have x equals to y equals to alpha and z is minus alpha. That means one of them is negative. So when we add all three of them, so basically two of them cancels out each other. So we'll be left with just 1. So 6 will be equal to alpha because plus alpha minus alpha will gets cancelled out. So in this case, we'll get under root minus lambda by 3 is equal to 6. Yeah, squaring both the sides, we'll get minus lambda is 3 times 36. So lambda is equal to minus 108. And hence, x equals to y equals to alpha, and alpha is under root minus lambda 108 by 3. So this is under root 36, na? So this is equal to 6, and z will be equal to minus 6. So the point will be 6, 6 minus 6, and in this case fxyz will be x cube plus y cube plus z cube, and clearly y cube and z cube will get cancelled out, so just the x cube. Yeah, 6 cube. So similarly, in fact, similarly for C3 and the cases where just one of them is negative, C3 and C4, also everything will be same, and in this case xyz will be in C4, in C3 the second term is negative, so this will be just 6 minus 6, 6, and in C4 this will be with same value of fxy with fxyz to be 6 cube, and in C4 xyz will be same 6 minus 6, 6, 6 with xyz, which is yeah, 6 cube is 36 times 6, so it will be obviously greater than 24. And then we are left with the case when two of them are negative. In that case, in C6, C5, x is alpha, y and z both are minus alpha. So again by star, again x and y will get cancelled out. We'll be left with 6 equals to minus alpha, which is minus under root minus lambda by 3, which is not possible because this right hand side is negative and left hand side is positive. So this is not possible. In fact, all the other cases. Similarly, this C6 and C7 are not possible. In fact, for C8 also. For C8 also, you'll get 6 equals to minus 3 alpha, which is again not possible. So the only possibility for the function's value to be were 24 and 6 cubes. So therefore, the minimum of fxyz, subject to the fact that x plus y plus z equals to 6. This is equal to the value of the function f at 6. Minimum is at 222. 222, which is 24, and the maximum is at 6 minus 6, which is 6 cube. So since 6 cube is not there in the option and 24 is there, so I'm hoping that this is a typing mistake. It should be minimum, and therefore the option B is correct. I hope the solution is fine with everyone. If you have any doubt, you can ask. I'll wait for 5 minutes, then we'll move to our last question. Okay, so if there is no doubt, we can move ahead. This is probably the last problem for today's session. This is question number 7. State whether true or false I think my screen is not visible. There is some issue. I hope my screen is visible. Uh, I hope my screen is visible now. Sorry for the disturbance. Okay, so we are left with just the last question. Okay, state whether true or false. 0 is less than equal to the integral, double integral over region R of the function sine pi x times cos pi y dA less than equal to 1 by 32. So basically we need to see whether this integral lies between 0 and 1 by 32 or not, where this R is equal to 0 comma 1 by 4 cross 1 by 4 comma 1 by 2. So let's just firstly see what the value of this integral will be. We have x from 0 to 1 by 4 and y from 1 by 4 to 1 by 2. So the integral I, which is equal to R sine pi x cos pi y, if I take dx dy, this will be equal to, so the value of y is from 1 by 4 to 1 by 2 and x is from 0 to 1 by 4 sine pi x cos pi y dx dy. This will be equal to 1 by 4 to 1 by 2. While integrating with respect to x, we treat the variable y to be constant, so it comes out. And the integral of function sine is minus cos pi x upon pi 0 to 1 by 4 dy. So this is minus 1 by 4 to 1 by 2 cos pi y upon pi. Now cos pi by 4 is 1 by root 2 and cos 0 is 1 dy. So this is equal to, taking LCM, this will be 1 minus. So this is just root 2 minus 1 by root 2 pi 1 by 4 to 1 by 2 cos pi y dy. Now integrating cos pi y, this is root 2 minus 1 upon pi root 2. Again, the integral of the function cos is, yeah, this is sine, not minus sine pi y upon pi from 1 by 4 to 1 by 2. So this is root 2 minus 1 by pi root 2 pi square. Sine pi by 2 is 1 and sine pi by 4 is 1 by root 2. So this will be again root 2 minus 1. So this is root 2 minus 1 whole square upon 2 pi square, which is obviously always positive because root 2 is 1.41, which is greater than 1. Again, since it's square, so it will be greater than 0 anyways. So therefore, one side of the inequality is true. So this much is true. Next, we need to see that whether it will be less than 1 by 32 or not. So firstly, let's see if it is, when will it be less than 1 by 32? Now, I, this is exactly equal to root 2 minus 1 square by 2 pi square. This will be less than equal to 1 by 32 if and only if, or instead I can write double-sided arrow, if and only if, let's just simplify things a bit. So this will be 32 times 32. Yeah, 32 times root 2 minus 1 square less than equal to 2 pi square. If and only if, just expand this a minus b whole square. So this will be 2 plus 1 minus 2 root 2 less than equal to 2 pi square. So that gives us that 32 times 3. Yeah, 32 times 3 minus 32 times 2 root 2 is less than equal to 2 pi square. We can take this, divide both the sides by 2. So this will happen if and only if 16 times 3 minus 16 into 2 will be again 32 root pi is less than equal to pi square. So this gives us 16 times 13 minus 2 root, 3 minus 2 root 2 is less than equal to pi square. So this happens if and only if 3 minus 2 root pi is less than equal to pi by 4 whole square. So this happens if and only if pi by 4 square minus 3 plus 2 root 2 is positive. So all we need to check is this value. Now if this is positive, then this will be less than equal to 1 by 32, and if this is negative, then that will be greater than 1 by 32. So that means the integral I is less than equal to 1 by 32 if and only if pi by 4 whole square minus 3 plus 2 root 2 is greater than equal to 0. Now let's check this. Pi by 4 square minus 3 plus 2 root 2. So we know the approximate value. No? The approximate value of this pi is 3.14 upon 4 square minus 3 plus 2 times root 2 is about 1.41. No? So this is equal to, if we take this square, this 3.14, this will be something 9.85, or we can say 9.86 upon 16 minus 3 plus 2.8, taking 16 to be LCM, 9.86 minus 0.18, just minus 3 plus 2.8 is 0.18 times 16 upon 16. So that will be 9.86 minus This is something 2.88, which is obviously positive. Now, since this is positive, this is always be positive because there is very high difference between 9.86 and 2.88. We can say, in fact, using this approximate value, that this will be positive. Now, since this is positive, that means I is less than equal to 1 by 32, and we already knew that this was positive. So, therefore, the given statement is true. I hope the solution is fine with everyone. Please go through this again. If you have any doubt at any point, please let me know. I'll wait for 5 minutes or else we'll finish this session. Okay, so if there is no doubt, we can finish this off. So we'll meet next Saturday. Thank you.